I'm Greg Becker, and as Todd said, I'm going to be talking some about the road to 1.0 in Spack. And here's a picture of Todd at FOSDEM in 2018 talking about how we were going to do all of this. And to the last point on putting our roadmap online, to some extent this talk is, here are all of the ways that you can be absolutely wrong about your roadmap. But that said, we mapped this out at a certain point, and we are nearing the completion of this large set of work that we mapped out. So what we wanted for Spack 1.0 is we wanted a new, more complete concretizer. We wanted better reuse for existing installations, more stable production environment, and most importantly, compilers as dependencies, and then a stronger package API and separating the built-in repo from the Spack tool. And I haven't gone in the last day and changed this stable package API line, but that is actually merged to develop yesterday morning. This is the biggest set of changes. The compilers as dependencies work, at the tail end of this, is the biggest set of changes that we have put into Spack. So I'm going to go back and start talking about some of the technical details from the whole way through this. And the idea is not necessarily to know how all of it works so that you can work on debugging it with us, although that would be great if you want to, but more that you know enough about how it works that you can be an educated user when you're using these features. So most of us, if we've worked with Spack some, we're pretty familiar with this. We have a DSL for declarative statements about the possible space of builds for a package. And this description can get very complicated very quickly, and is only getting more complicated as more packages support CUDA and ROCm and things like that. So the first challenge is we needed a concretizer that could effectively model all of this and would not have to just give up and say, I can't find a solution for things that could be built. And there's a lot of information that has to be synthesized for this. It's all of the config files, the entire package repository, and what the users actually requested. This part is NP complete. So that's also a concern. Can we make this perform reasonably? And we'll talk more about that later. So we started out with our own greedy solver in Python. It performed fine, but it was often incorrect. We looked into SAT and SMT solvers for this, and to varying degrees, these were going to be very difficult to encode the Spack solve in these languages, especially with SAT, but even with SMT. And so then we ended up choosing answer set programming, which Klingo is the program from the Potasco project. And it looks something like Prolog, if you're familiar with Prolog. It's pretty easy to read once you get used to it. And it has some very good support for optimization criteria for choosing the best solution. And it has a huge advantage over Prolog that it is guaranteed to terminate. So the new concretizer is implemented in ASP. There are facts that describe the graph, things like there's a node lamps, there's a node CUDA. Lamps has its CUDA support turned on, and there's a dependency between them. And that's a notional ASP program describing those relationships. These examples will get more complicated and closer to the true complexity of the solver as we go along. And then there's rules that describe how you interact with this, or how these facts interact with each other. Things like, if you have a node and it depends on something, you better have a node for the dependency. All right. Integrity constraints in ASP are how we say this cannot happen. So for cycle detection, you can say if there's a dependency between two things, there's a path. If there's a path and a dependency, you can extend the path. And no cycles. We'll come back to this one later. There are choice rules in ASP as well, which allow the solver to kind of generate new facts. So if you've got a bunch of possible versions, you can have this rule at the bottom here that says there is at least one thing in this set, and we'll talk about the set later, but there's also at most one thing in it. And if there's a node, we've got a set like this, and this is choose a version. You can create this fact out of thin air with the constraint that it has to be from the possible versions. I forgot I had coloring for this. So maybe the coloring will make what I just said a little clearer. And then the last kind of feature of ASP that we use rather heavily is optimization. We can associate a weight with each version. And then we can say, for every package, it has the weight of its version. And then we can minimize across all these weights. And we always do minimization. There's no maximization in the solver because you get really wonky answers if you do maximization, because the solver will just say, I can turn on your variance and add more nodes, so I get more opportunities to maximize it. So ASP searches for answer sets or stable models, which is basically like a fixed point. It's any set of facts for which the rules don't change it. And I mentioned before it's guaranteed to complete. So what's in the Spack solver? There's a setup phase. Basically, we take all of the facts from our Python files and we turn them into ASP. Then ASP does grounding and solving. Grounding is turning the ASP format into SAT, and solving then does what's on the tin. And then we reconstruct the solutions from that model set back into Spack specs. So what is grounding? Take a very small program here that just does the things we've talked about dependencies generating nodes. And then we say there is at least one of these nodes, node A or node B. The grounder is going to go through and it's going to say, OK, if node A, then node B. If node A, then node C, et cetera, for all of the possible combinations from this depends on rule. And then at the bottom, that one's actually not grounded in this example, but you could say, A or B, right, for at least one. And then when we solve it, we say, OK, there's one answer that solves this where B is true. And there's an answer where A is true. And that guarantees the whole graph. The logic program is about 250 of these rules. Like if you have a node and a dependency, you need the other node. 20 to 50 optimizations, depending on how you want to count exactly. It's around 1,200 lines of ASP. The solves then will have hundreds of thousands of facts generated from the package.py files. And the grounded program will have, we're generally saying, roughly 1 to 3 million grounded facts. This can make complicated logic very simple. It's also hard to think about sometimes. I'm not going to go into the details on this one. We use these optimization criteria that I mentioned to try to find the best solution, where best is defined by we've written a set of criteria that is designed to mimic user intuition about what you want to build. Getting that right is unintuitive, and there are still places where we're not completely happy with it. We'd like to have precedence based on how far from the root you are, but that's a technical challenge to make that perform. So that was challenge 1. Challenge 2 was reusing the existing installations better. So the old concretizer, you'd concretize your program, you'd get the hash for everything, and then you'd check either a cache or your existing installations for whether they exist, and you'd reuse it if they existed. And that was fine, but really, if you installed HDF5 earlier today, you probably want to use that one again, regardless of whether it's the default concretization. So the new concretizer allows us to be more aggressive with this. First, we take all of the installed packages and we write them out as ASP facts. And then we can say, okay, if you have something in the graph, you can choose at most 1 hash for it. If you choose a hash, you have to impose all of the facts related to that one. If you didn't choose a hash, you have to build it and minimize the number of builds. And that takes us from a situation where you could try to install HDF5 and have no reuse at all to just turning the reuse feature on. 16 of those packages, we've actually got a build that you can use. It might not be the most default one, but it's there. So there's this weird bifurcated optimization criteria. What's up with that? This is where Klingo is a little bit of an art. We want to prioritize reusing a package. We also want to prioritize when we build something, building it in its default configuration. Right? This is what we as people who install things think of as just kind of the default thing to do. It is not the default thing to do for the solver. The solver is going to minimize builds. It's going to say, I can turn off this feature, and then I don't have to build as many things. We don't like that. So how do we do both of these things at the same time? The answer is we split the criteria. So there are duplicates of every criteria for things that are being built and for things that are reused. And we interleave these so that the optimization on the number of builds comes in between them. So if you can reuse something, you don't have to care as much about how it was built. But as soon as you can't reuse it, those priorities go up. And I mentioned before, to get this all to work, everything has to be minimization. So this performs reasonably well. The graph here is showing the total solve time by number of packages for the old concretizer and the new concretizer. So a little bit worse performing than our greedy Python algorithm, but it's also much more correct and does a lot more for us. And it scales reasonably well over the number of packages that we're reusing. So now this is scaling up. How many things do we have in a binary cache? How does our solver performance go? And it definitely slows down, but even with 63,000 packages in the example on the right, individual solves are taking seconds. If you solve a large environment, it can be a little longer, but we're reasonably happy with that. So our third challenge is to get to compilers as dependencies, we needed to be able to have multiple versions of build dependencies in the graph. And this makes sense, right? People will build part of their graph with GCC and part of it with one API, and those are both providing the C, the C language as a virtual, and we need to be able to do both of those in one graph. This is also important for Python, where things like PySetup tools or PySython are often at very restricted versions for individual packages. And so it's very easy to run into cases where you can't get away with only one build dependency for your entire graph. You have to have some way to split it. So the objective is to look at this and say, well, okay, if these are build dependencies, they're not there's no need to unify those, right? For link dependencies and run dependencies, there's a unification constraint based on either the loader, right, which is you get a loader race otherwise, or with run dependencies, right, there's a name spacing problem. If you stick everything in your path and you call the name, you need to know which one you're going to call. So we went into the solver and we said we want to dynamically split these nodes as needed. So this choice rule here says, okay, if you have a dependency and the dependency holds, you need to depend on something. And for each package, we're going to put in a maximum number of times that package can occur. And you can pick which duplicate of that package to use. And this is the final result of a lot of work to get there. We'll talk about some of that. And then we re-encode everything so that it's associated with those duplicates. And our first attempt at this performed horribly. And I should say this was not our first attempt at this. This was our first attempt at this that worked and that could complete before the heat death of the universe. But it still performed horribly, greater than 2x. And so we started thinking, well, how can we optimize this? One thing is cycle detection is expensive, right? We looked at this little bit of cycle detection code earlier. And it's got to maintain a lot of data between nodes. And anytime you're dealing with a relationship between large numbers of nodes, you've got an exponential explosion in this NP-complete problem. So we turned it off and did post-detection for it. But it turned out when we talked to the Klingo developers, they're tracking all of that information internally also. And we could rely on some fancy stuff there. That's a 50% improvement in the solve right off the bat. Now, this isn't specifically related to dependency splitting. But we did a variety of these sort of general performance improvements to go along with the feature. We basically said, OK, we've made the solve more complicated. We're going to find all of the low-hanging fruit for performance, or maybe the medium-hanging fruit for performance. And we're going to fix all of those at the same time so we can get this more complicated solve in without torching the performance as users see it. So another one is these unification sets become expensive. You're basically doing a whole separate solve for each unification set. And so what we did is, OK, we know which tools generally need this. We created a configuration scheme where you can say, here's how many duplicates you can have for PySetup tools. Here's how many you can have for CMake, things like that. And if you're not able to solve what you need with that, go bump those numbers up. Great. But by putting some limits on it, we were able to get better performance as well. So cycle detection, unification sets, we improved our encoding for variant propagation, and we improved how we built Klingo itself to make the solver itself perform better. And we were able to get a whole lot of performance back out of it. So in the end, we got this feature in with improvements to performance overall. I mentioned we tried a lot of different ways of doing this. Here, this is a notional diagram of an iterative approach we were looking at, where you concretize the link run subgraph, and you forward the build dependencies to a separate solve, and then you solve those. But there were these, in red, you can see these like errors where you're feeding back information, and then you would have to resolve it again, because if I solve something and, okay, now I need CMake 3.26, oh, but CMake 3.26 doesn't build on this system, feed it back, now I've got to redo the whole thing. It wasn't feasible that way. So with all of that, starting after ISC last year, when we released 0.22, we were finally ready to start working on our project from 2018. And so in the latest release of Spack, we added language dependencies. So packages expose which languages they depend on. Do I depend on C, CXX, Fortran? Earlier in Spack, it was just assumed everything had a compiler, and that compiler provided C, C++, and Fortran. And okay, you're going to duplicate your builds of some pure Python stuff, but oh well. So with this, well, in 0.23, this was just so that you could start porting, but moving forward to develop now, you don't have to associate a compiler with your pure Python packages, because that's not how they build. So that finally brings us to compilers as dependencies. And for this, in the picture on the right, the blue dependencies are build dependencies, the red are link dependencies, and the green box at the top, zlibng, about the simplest package we can find, is what we requested. The blue boxes are the things that it depends on, and then the gray boxes are the things that the Spack solver adds into the dependency list implicitly based on the dependencies on the languages. So the solver knows, okay, if you are building with GCC, there's a relationship between GCC and its runtime libraries, such that if you use GCC for your C or C++ compiler, you also need a link dependency on the runtime libraries. Similarly, you need a link dependency on glibc, right? Basically at the bottom of everything, there's a dependency on glibc. And then the third one is the compiler wrappers, right? Spack has a set of compiler wrappers. Typically, they had been part of Spack itself, and we've separated them out to be their own package that gets injected. The idea with some of this is that eventually you could even swap out glibc and use musl if you wanted to. We're not going there yet for 1.0, don't worry. This has changed how we specify the compilers to Spack. In previous versions of Spack, the compilers were kind of a one-off object that you configured in a separate file. In 1.0, they're going to be configured like any other external package that you use. But we're not going to stop reading the old one. You don't have to migrate immediately. At least until 1.1, we're going to keep reading the old format. So what are the breaking changes here? The biggest one is it is no longer safe to assume that everything has a compiler. So if you're writing a format string for your install tree layout, or if you are accessing fields inside the package build, you can't just say, give me my compiler. Now, if you do, we're going to say, OK, you probably mean the C compiler. And if it doesn't depend on C, I guess you meant the C++ compiler. And if it doesn't depend on either of those, I guess you must have meant the Fortran compiler. And we won't throw the error unless it really doesn't depend on any of those. But instead, you'll need to say, OK, give me my C dependency, my dependency that is providing C, the same way that you would for my dependency that is providing MPI. The second one is subscripting a spec will not search through transitive build dependencies anymore. It's only going to search the link run dependencies and the direct build dependencies because that's the unification set for that package. If you need to go into a dependency of a build dependency, you can do that. You just need to be explicit about what you're doing. And the percent sigil that we've always used for compiler now is going to have two meanings. One, it's going to mean direct dependency of any sort. And two, it's going to mean tool chains, and I'll talk about that later. With the change in the syntax, there's also a change in the ordering that you need to do. So previously, you could order the variants and the compilers and the versions any way you wanted, and they'd all be read as part of that node. Now that the compiler is not part of the node, it's going to follow the same sorts of rules that the dependency sigil already followed, where once you specify a dependency, everything after that is affecting the dependency, not the root spec. So package %gcc plus foo is now going to be trying to build gcc plus foo. That's not a variant on gcc, and you're going to get an error. Getting an error is the best case scenario here, because if both packages have the same variant name, you'll just silently build with a gcc built with that variant. So you're going to need to reorder these. And we have a Spack style command in the current version that you can use to fix this in YAML files, package.py files, etc. This is finally done. It's been in develop for about a month now. And thank you. A lot of people have already started using it, finding problems with it, letting us fix bugs before we cut a release and get embarrassed by the bugs. So again, thank you. It ended up being a net reduction in code. So lots of special handling for compilers that we were able to get rid of. So we were very excited about that. All right. So the last thing for 1.0 is splitting out the package repo, right? Spack, two things. There's the core tool, and there's all the packages. And the coupling has typically been pretty tight between those. The build system base classes that the packages inherit from are part of the core tool currently. We're going to separate those out, put them in the built-in repo. The compiler wrappers I mentioned have become their own package. There's some other things where packages are currently tied to, when you install a package currently, if you're going to load it, you need to have a version of the package.py file that was compatible with the package at the time you built it. We're moving to install little load files with all of the packages so that they can be independent of the repo, and if you lose track of the repo, you can still Spack load the things you installed with it. And then there's the more engineering constraint of they live in the GitHub repository. It's not easy to separate. I mentioned all of those already. So what's left? We're going to add a larger concept of a tool chain. This was not something we identified when we went through what this was going to take before, but we started showing people the compilers as dependencies work and the syntax for how you can get really detailed about, okay, I want to build with GCC satisfying my Fortran compiler, but I want Clang to be the C and C++ compiler. And the syntax for that works, but it's complicated, and all of the users that we showed this to said, yuck, please don't make me ever type that. We're not going to be able to make you never type it, but we are going to make it so that you type it once in a config file and you say, this combination of constraints is my toolchain, or my GCC toolchain, or my second favorite toolchain. And then you can just refer to the toolchain on the command line, and it's going to be, a parse time alias. It's just going to swap in the text, basically, of what you configured. So that should help, right? You're a power user. You support some less Spack knowledgeable users. You write out these toolchains for them, and your users never have to think about that complicated syntax. There's a few places in Spack where we haven't been able to separate the packages from the core yet, so we're still working through those. And especially our testing infrastructure, we need to figure out which tests are talking about the built-in packages, but really they're testing the core, and we need those to be rewritten so that they're not dependent on the built-in repo, and which tests are actually testing the packages, and those tests need to be migrated to the new repo. So that's where we're at, right? We've merged compilers as dependencies. We're working on splitting out the package repo. Some major work for that went in yesterday morning. We need to iron out any issues with, how do we get the two GitHub repositories and make sure they're in sync. The toolchains work that I mentioned, all of that we're planning to do this month. And we're going to release Spack version 1.0 at the Spack BOF at ISC. And we're going to run the tutorial on Spack 1.0 at ISC. All right, that's all I've got. Any questions?
So it was previously possible pre-1.0 days to use Spack outside of an environment to build a compiler and use that compiler to instantiate everything that goes inside of that environment. If you try that on the current develop branch, as of yesterday, you can get into this really nasty, it takes forever to solve and then just gives up after 2 hours if you try to do that because it tries to impose the wrong GCC runtime libraries. Is that something that's on the list of things to fix? Because that's a pretty important use case.
So first, yes, it is on the list of things to fix. Also, if I understand what you're referring to correctly, you can also point Spack to the Spack-built compiler as an external and navigate around the problem, which is effectively what you did before, right? You pointed Spack at the physical path to it instead of relying it on as a Spack install. And if you do that still, it should avoid that bug, but we are hoping to have it squashed for 1.0.
The thing we may not do is, if you specify that, we may not be able to solve and build the first compiler automatically. But, I know, I think most people don't care about that. However, we will be able to fetch the first compiler from a build cache. And so you essentially could have a build cache of GCCs or Clangs and then throw us back on a machine that has no compiler and take an environment and just build it from scratch, which I think would be very cool.
There's another question back there.
So you said that the compilers would now be built on the dependencies. Sometimes with JIT code, you would need compiler to also exist in runtime in a separate way, and then
so you don't have to depend on it as a build-only dependency. Most codes do. If you're running something with JIT or if you're linking against libllvm, right? You could have a runtime. JIT code has a runtime dependency on the compiler, and something that links against it has a link dependency. Just encode that the same way you normally would. If you do that, you're only going to be able to have one compiler in the link run subgraph, but if you try to have more than one in the link run subgraph, you're going to have a bad time anyway.
Can you go back to the diagram of, it may be a ways back. Yeah, here.
So there is nothing stopping you from having the edge from zlibng to GCC be, link type and or build type and run type, for example, for a JIT code.
Yep. and I guess you can see it here, but the package depends on this through the virtual as a build dependency, right? And then actually, like the runtimes are decided entirely by the GCC package or the compiler. And that was intentional because it allows the virtuals to abstract the language implementation, right? And so this guy decides that you need GCC runtime and a C implementation here, right? And then those end up being linked dependencies, which means that they're unified in the graph, which is what you want for the runtime libraries. And so that's it. It's complicated, but it puts, I think, the maintenance for the different things in the right place.
But to get back to the question, if you have a runtime constraint, right? If you're running the compiler at runtime for just-in-time compilation,
Yes.
just tell Spack.
How much effort would be involved in introducing like a new language compiler that has a JIT? So for example, Julia, if we've started producing Julia packages, Julia code, things that will both, can be pre-compiled, but other things that need to be JITted. Is that sort of thing already covered in the design and it's a relatively simple addition? Or is that serious news design work?
We believe that it's already covered in the design and relatively simple addition. But with no one having played with it yet, I'm a little hesitant to say that with a lot of confidence.
Yeah, I mean, the point of this was to say that like the only compilers in the world are not C, C++, and Fortran, right? Like there are others, and we wanted to make that easy. Let's try to get one in, and we'll fix bugs to make it possible.
I noticed you mentioned that Spack was going to get a concept of a tool chain, and I'm wondering if there's some synergy there with the CMake concept of a tool chain, and could we maybe share some concepts there?
I think that the best we could do there is find a different word for it so that people don't think that we should. It's pretty different. It's just a collection of dependencies, but
I like that answer.
On a related question to CMake toolchains, oftentimes when you're doing cross-compilation, you need a separate host compiler and a separate target compiler and a separate sysroot for those. Does the current design facilitate separate sysroots and host compiler versus target compiler?
So we don't have a picture of it, but in 2019 we had a meeting with folks from Recon, and we mapped out everything that it would take to support full cross compiles, and that maybe the picture of me and Todd at that meeting should go next to the one from FOSDEM where we said, yeah, first we just have to do this compilers as dependencies stuff, and then we can talk about the node splitting where the same node has to appear on both architectures to get the build system to accept it. All of that is, we still want to do this, but it's all been, this is what we work on after compilers as dependencies since we first talked about it in 2019.
It's on the roadmap after 1.0. So we've got about a year dedicated to cross-compilation in the roadmap. So, anybody else?
Doug's up here.
Oh, okay. Doug was first.
How does the governance of the package repo relate to the governance of the core repo?
So the project is, we're still running it as a single project with two repos. So the governance in terms of the technical steering committee is all the same across both of them. I would say there are a lot more people who have full deep understandings of the package ecosystem than the core tool. And so there's a lot more people who can do code review and support a high velocity of changes in the package ecosystem.
But I mean, the current TSC was chosen from core contributors and package contributors, so like it's not going to change the governance. I think that we're going to keep them intertwined, but they'll be separate repos.
So we use a wrapper around the Spack Python, and I'm just wondering, is there a way to incorporate like more modules into the Spack Python? Because oftentimes we need to use inline Python in our workflows, and then modules like netcdf4 or NumPy, they don't come up. So if I load like a wrapper stack Python and just module not found, and so using these like pi dash whatever modules aren't really amenable for our workflows. Is there a way to have more modules built into the core? Like it's not a Conda installation, obviously, but am I missing
So,
something? Because it's been
yeah,
a
I
problem
think-
that I can't quite figure out.
I think this is something that's unrelated to the compilers' dependencies. Things like Spack environments with a view where your Python gets symlinked into the same location as all of the Python packages that you're using with it. It is designed to eliminate the problem you're having, whether you found a case that it doesn't work for or whether we haven't found exactly what you need to be doing to use it is an open question.
Well, he said he doesn't want to use necessarily the Spack pi dash packages, right? And so like you can just make a virtual environment and install the stuff that you want, and then point the Spack Python environment variable at that one. And then if you run Spack Python after that, it'll come up with that Python interpreter and whatever site packages you have in it. We don't disable site packages. So you can do that. Okay, but I think the break is happening, so we should probably adjourn so everyone can get coffee, and then we will be back for some more core dev talks afterwards. So thanks everybody, and feel free to catch us after.